Let's assume that you're looking at one pixel in the image right here. This pixel projects onto some area on your surface. Now, within this area, it's hard to assume that the entire patch that you're looking at, the physical patch, is perfectly smooth, irrespective of whether the mechanism is surface reflection or body reflection. It's going to have some roughness. That's the way surfaces are. It's going to have some roughness associated with it. So we want to come up with a way to model the roughness of a surface and then see how that ends up changing the reflectance model, be it for a Lambertian surface or material that is Lambertian or specular. So let's model surface roughness. One simple model is to use what's called a microfacet model for the rough surface. So imagine that the surface is made of a lot of these tiny little facets. The surface itself has sort of a mean orientation, which is n, but each one of these facets could have its own orientation alpha. So now you can describe the roughness of the surface using a distribution. In particular, Gaussian microfacet model uses the Gaussian distribution, where the alpha, or the tilt of each one of these facets, is described by the Gaussian function. And it has a standard deviation sigma right here. So the greater this value of sigma, the more rough the surface is going to be. Imagine that sigma is equal to 0, then you have all the facets looking straight up in the direction of the mean orientation itself. You get a perfectly flat surface. So that's what you see here. You see sigma equal to 0, you get a perfectly flat surface. Sigma equal to 0.1, it starts getting a little bit rough. Keep increasing sigma and the roughness increases. So what's been done in the past is that this kind of a surface model has been used along with both the Lambertian model and the specular model, meaning that assumptions have been made that the facets are either perfectly mirror-like or perfectly Lambertian, and then one can ask the question, what is the reflectance of the aggregate reflectance of the entire patch that you're looking at? So that brings us to the Torrance and Sparrow BRDF model, where it is assumed that every facet within this microfacet model that you're looking at, every facet is a perfect mirror. But each one of these facets can have its own little orientation. And when you calculate the BRDF, you're calculating it for the entire ensemble or collection of facets. And so this is the BRDF that was derived. It's a very popular model where you have rho S up here. Rho has to do with the reflectivity of each facet. Remember that even though it reflects like a mirror, it doesn't mean that 100% of the light that it receives is reflected, so you can have mirrors of different qualities. So that's what this rho S is. And P right here is the microfacet orientation or roughness model that we just talked about. It has sigma here. Sigma relates to the roughness. And then you have this function called G. This G is called the geometric factor or geometric attenuation factor. And it takes into account various geometric effects that happen when you have a surface that's not flat. So imagine that you have a V groove that looks like this. You have two facets. So in this case, if lighting is coming from this side, one facet could cast a shadow on the other facet. And if you're observing it from some direction, one facet could actually mask the visibility of the other facet right here. So this function takes into account all of these effects, and that's why it shows up right here, and this is the BRDF that you end up getting. And what's nice about this BRDF is that when you set sigma equal to 0, you get the BRDF of a perfect mirror, a specular surface. So let's see how specular reflection from a rough surface works. This is our same setup as before. This is your sphere. This is the viewing direction, this is the source direction, and we are again assuming here that these two, the camera and the source, are really far away from the sphere. So if you have sigma equal to 0, you get exactly what we had for the ideal specular case that we saw before. You get a single bright spot at Q, this point right here, which has a surface normal, which is the bisector of these two vectors, V and S. If you increase sigma a little bit, you see that you start getting this lobe. It's what we call a highlight, a lobe right here. You increase it further, and the lobe starts getting broader and broader. One of the interesting things about this Torrance and Sparrow model is that in this case, when you have a fairly rough surface, the brightest point is not Q. It's usually a point that is further away from Q. It's on this side, on the right side of Q. And that comes from all of these geometric effects that we talked about, masking, shadowing, and so on. So that can be used to actually visualize how a scene might appear when it is reflected by a sphere, which is specular at every point, but has some roughness to it. So in this case, it is a perfect mirror. It is a sphere that looks something like this, right? It's a perfect mirror. And then as you increase the roughness, you see that the scene ends up looking more and more blurred. We've all seen this before. And in fact, it starts looking something like this. If you can see this particular sphere right here, you see that you can actually take a look at this and guess where the light sources are, but the rest of the scene has been blurred out, so to speak, because of the roughness. Although it is primarily surface reflection that's taking place here, meaning to say that there isn't any body component. There's no Lambertian reflection happening here. If you further increase the roughness, you see what happens. Things start getting blurrier, and so on. And then at the other end of the spectrum, you can play the same game. What you can do is now say that you have the same microfacet model for the surface, but rather than assuming that each facet is specular or mirror-like, we can assume that it's Lambertian. This can also happen. You can have rough surfaces which have primarily body reflection, where each point can be assumed to be Lambertian, but when you look at a chunk of the surface, which is what the pixel projects onto, it is a collection of these Lambertian facets pointed in different directions. So in that case, you get this BRDF. We don't need to go into the details of this. And once again, when sigma is equal to 0, this actually reduces down to the perfect Lambertian model. So let's take a look at what happens in this case. Here you have the same setup, distant viewer and source, and when sigma equal to 0, you get exactly Lambertian reflectance. This is what we call a Lambertian sphere. As you start increasing sigma, you see that the sphere begins to appear flatter and flatter. If you look at this area right here, you see it's not quite as bright as this area right here. So this is an interesting effect which is particularly pronounced when the viewing direction and the source direction are the same. So here you're seeing spheres that are illuminated and viewed from the same direction. And in this case, where you have sigma equal to 0, you get a perfect Lambertian sphere. You see that you have a bright point here, and then the brightness falls off rapidly towards the edge. As you start increasing sigma, something interesting happens, which is that sphere begins to appear flatter and flatter. In this case of sigma equal to 0.3, you see that the sphere begins to appear more like a flat disk, like a cutout disk. And indeed, that is the phenomenon you observe in the case of the full moon. It's known that the surface of the moon is very rough, and you may have noticed that the full moon doesn't look like a shaded sphere, like a Lambertian sphere, but looks more like a flat disk. And that it is hypothesized is because of the roughness of the surface of the moon.